Hello. Is it audible now?
Yeah, perfect.
Let's start.
Raise the mic to introduce.
Okay, we'll leave this.
Hi everyone, welcome to the class of CS772. Today we have with us Jimut. He's a fourth-year PhD student at the C Minds Center for Machine Intelligence and Data Science, IIT Bombay. His research is supported by the PMR scholarship. He's advised by Professor Suresh Abate. His research lies in the intersection of deep learning and computer vision, with a particular focus on medical image segmentation. He designs robust, interpretable, and efficient algorithms that address key challenges such as data scarcity, computational constraints, and heterogeneity in medical imaging. So, over to you, Jimut.
Thank you. Hello. Okay, so today I will be talking about convolutional neural networks. So I might take around 10 to 15 minutes extra. So this is we have to cover a lot today. So these are the contents that I'm going to cover. So firstly, I will be talking about images, like ambiguity of images, a bit of history about CNNs, then CNNs in general, then the technical aspects of CNNs, and then parameter calculation, and like some of the most prominent architecture from CNNs, transfer learning from CNNs, and I will be showing a demo about multi-class image segmentation. So for this demo, it will be taking around 20 minutes, I guess. But let's see. So now let's talk about images, matrices, and ambiguity of images. So what are images? Like how many of you have done CNNs before? Okay. So images are like 2D representation of visual information composed of pixel, each containing specific color or intensity value. Like for example, this image of main building in grayscale will have 2D matrices as its representation. So digital images are matrices of discrete data, like for example, photograph, video frames, etc. And in general, natural images are normally 3-channel or 1-channel. So this is 1 channel because it is grayscale. And if we are having natural images, it will be having 3 channels, like 1 channel for red, 1 channel for green, and 1 channel for blue. So in general, like if you are using NumPy or OpenCV, it will be represented using 2 to the power 8 values, like each of the pixels. So it starts from 0 and ends at 255, the intensity values. So say, for example, if you are taking this image and taking the top left corner, like here we can see 10 cross 10 pixels, this is the content. Similarly, when we are dealing with deep learning architectures, we will be specifically using torch.float32, which is the default, since there will be real values, not specifically integers. So images are often normalized between 0 to 1 intensity before passing into DNN models to stabilize the training. So this is a 3-channel image. Here, when we are selecting the first 5 plus 5 pixels, we can see it is composed of 3 values. So this is an individual pixel value, 224, 198, and 128. So something unrelated, like images can often be ambiguous, like almost like a natural language text. So for example, there is like puppy or bagel, Shiba or marshmallow. And even the human perception is somewhat varied by like some illumination constraint. So for example, what we can see here is like there is a illusion of a triangle. So there is no specific drawing of a triangle, but there is a void in here, which give us a illusion that there is a triangle in it. And there is a French caricature of Napoleon III. When rotated, it will turn into a donkey. So there are some ambiguity in images as well, just like NLP. So a bit of history about CNN. So firstly, Hubel and Wiesel studied about responses of a cat's brain when they presented the cat with some of the images. What they found was that the cells are organized as a hierarchy of feature detectors with higher level features responding to patterns or activation in lower level cells. So the main information that they get was like the cells are organized in hierarchy. So like simple cells will be having low level features, detecting low level features. Then complex cell will have mid level features, and higher or upper complex level cells will have higher level features. And some other history is like mostly what happens in deep learning in general is there is like golden age, then there is like dark age, then is golden age, and dark age like AI winter. So ZOR problem, the famous ZOR problem was causing the first AI winter. Then popularity of SVMs and other stuffs caused the second AI winter, because back in 1980s to 1990s to even 2000s, most of the researcher focused around those methods which were explainable. And AI winters are generally like triggered by inflated expectation and disappointing results, which led to funding cuts and fading interest. So now is mostly the golden era of deep learning, since there was a Turing Award, which were awarded to Bengio, then Hinton and LeCun in 2018. And also like Hinton and Hoffield got the Nobel Prize in physics for this development in like for the contribution in artificial neural networks. So the first architecture which contributed to the boom of deep learning was this AlexNet. So this AlexNet was proposed in around 2012 or 11 to 12, around that time, and it won the ILSVRC ImageNet challenge. So it was the first DNN architecture which used GPUs. So it used like two NVIDIA GTX 580 GPUs, which were low-end GPUs. Like back then, they were like very high-end, but nowadays this is very low-end GPU. So it has like 3 GB VRAM for each of the, and it trained for 5 to 6 days using C++ CUDA code. So they didn't use any torch or any kind of PyTorch or wrapper like that. So they coded it in C++ and CUDA. And this is the architecture which used ReLU, then convolutional layers, dropout, pooling, etc. And it was around 60 million. So this architecture, they won the this ILS VRC 12 challenge with an error rate of 15.3%, and the second one was around 26.2%. So this is the error. So previously what happened was like previous method used some sort of feature detection or handcrafted features. So they were using some statistical models. This was the first model which won this challenge using deep learning architectures. So one interesting fact about this AlexNet is it had 11 cross 11 filters, and all other methods after this AlexNet in that same competition had deep learning based modeling for winning. So there was like initial resistance to this revolution as well. So people were very skeptical about CNNs back in 2012, 2011, because CNN wasn't that popular. So here Jan LeCun is ranting about a rejection. So he didn't use fully automated like pipeline, end-to-end pipeline for CNN. He just used CNN in a part of the model, and they use some sort of graph and extraction modules for a paper. And what he found out was it was like having definite reject, borderline, and weakly reject as commits. So the first model which was trained on MNIST dataset. So LeNet 5 was the first model which was a proper CNN architecture. So AlexNet is a derivative of it, which was only trained on GPU. So the main functionality of AlexNet is it is just trained on GPU, and that is the reason they are scaling it up on high compute resources. So for that reason, deep learning boom actually came into existence. So now there are like many tasks which are traditionally like done by image processing or statistical techniques are being replaced by CNNs. Like for example, many tasks on image processing, then feature detection, 3D shape recognition, etc. are now done by mostly deep learning architectures. And this task has like inherent challenges which are present in images. Like for example, illumination conditions, then scaling, variation, deformation, occlusion, etc. are all present inherently for this challenging tasks. So now let's talk about the technical aspects of CNN. What is convolution? So convolution is the area under the curve f of tau weighted by g of t minus tau. So in continuous case, convolution can be written as an combination of integral with going from minus infinity to plus infinity and convoluting this two operation. So the terminology is like this f is the input, this g function can be referred to as kernel or filter, and the output is the feature map in general. So two example of convolution function are shown. Here we can see that the red one is the filter and the blue one here like this, and here is also a blue one. So these are the input, and the red box filter which is moving, it is the kernel or filter, you can call it. And the feature map or the response is the black one. So different kind of input will have different kind of feature. So what is like in general CNN? So CNN is CNN or convolutional neural network is using convolution in place of general matrix multiplication in at least one of the layers. So here what happens is this filter component is learned. So the CNN like indicate that the mathematical operation convolution is used, and in general in case of ML we use like discrete data points. Since like data is sampled at regular intervals and mostly we deal with real numbers or integers. So the convolution can be defined like this in discrete space. But what happens is like the input data set is usually a multi-dimensional array or tensor. And in practice, the outputs of the kernel are finite dimensional. Hence, the values are taken to be zero outside the finite set of points. Hence, this is not an infinite summation. This is like a finite summation. And in 2D, convolution can be mathematically represented like this in here. Okay, so now let us see an example of convolution. So convolution is nothing but like element-wise multiplication, just like dot product of vectors. So this is an input. You can see it. This is the gray thing is the input. This is the filter. What we are doing is we are taking a patch of the input, which is having the same dimension of the kernel, and we are doing element-wise dot product, like 4 into 2 plus 2 into 1 plus 7 into 2 plus 1 into 4, and so on. So after the addition, we will get output, which will be replaced in here. So 91 is the output. Similarly, for the next step, what we will do is we will shift 1 pixel to the right side, and we will perform the similar dot product, and it will be like 48 output. And it will go on till the whole part of the image is covered sequentially. So what we can see is that the 2D representation of the image has been saved here. So in general, like there is, so some of the key aspects of CNN are, it has like sparse connectivity. So traditional neural networks layers have separate parameter for interaction between each input and output unit. So in CNN, the kernel preserves the 2D spatial structure of input image. So we can see that this is also in 2D. By the way, you guys have learned about like fully connected layers, etc., right? Backpropagation, everything is covered. And transformer is not covered. Transformer is covered. Not covered, right? Covered. That's a gas lecture transform. Okay, by the way, one thing to note here is like everything is being replaced by transformer nowadays. Like CNN is not used that much. Like most of the architecture or the state-of-the-art architecture are replaced by transformer. So something like so key aspects of CNN. So there is like sparse connectivity. So in the sense like traditional neural network have separate parameters for interaction between input and output units. And in CNN, kernel preserves the 2D spatial structure of input image, as we have seen here. And in CNN, kernels are used, which have smaller size than that of the inputs. Hence, the number of parameters are much less. Hence, there is a lesser chance of overfitting. and fewer operations are required to compute the outputs. Hence, less training time for models. So there is like sharing of parameters. So in traditional neural network, a parameter is used only once while evaluating the output of a unit. And in CNN, the same set of parameters are used for all the units. So we are seeing that the same kernel, it is just moving around all of the image. So there is like less number of parameters. If this was a fully connected layer, all of these pixels would be connected to the next layer. So in CNN, the same set of parameters can be used and do not need to learn separate parameters for every input, only need to learn the same set of parameters for all the input. So here is a comparison of parameters for like a fully connected layer and say a convolutional layer. So for convolutional layer, what we will see is, so there are 9 as input and there is 4 as output. So if this was a fully connected layer, what is the parameter? So parameter would be like 9 into 4 plus 4 as a bias, because this layer will have 4 neurons. So each of the neuron has 1 as a bias. But what happens when we are using convolution is, say we are using a CNN with four pixels. It will be like this one is red, this one is blue, this one is yellow, this one is green. So same thing will be convolved through the whole input. So the number of parameters will be like 4 plus 1 for bias. So each filter has 1 as a bias. So ultimately there is a 8 times reduction in parameters. So if we are representing this in fully connected layers, it will be having a parameter of size 40, like parameter count of 40. And if you are using CNN or convolution, it will be having a parameter of only 5. And in images, what happens was like what happens in general is like if you are using 3-channel images, color images, it will be having 256 cross 256 cross 3, which is like 196K pixel. So if we are using fully connected layer, so there will be parameter explosion in very few layers. So in general, when we are dealing with images, we use convolutional neural networks. So some more key aspects of CNN are like CNN is equivalence to translation. So if the location of the certain feature is changed, then the output of the convolution also changes accordingly. And what is a feature? So feature is like pattern, characteristics, or attribute extracted from input data, such as age, texture, corners, or shapes, which helps in pattern recognition. For example, this is the kernel or filter, which will be applied to an input, and it will detect some sort of edges. So these are the features. Or it may like enhance the image, like sharpening. So this is the sharpened version of the original image, or they're just doing box like blurring using box filter. So in general, in image, what happens is like same feature can occur at multiple locations in the input space. So the output of the convolution indicate whether different features occur in input space. By the way, I am like writing everything in this slide, so this will be helpful when you revise, right? Because in general, mostly I will be skipping, but yeah. So next is like, for example, an edge detecting filter will generate 2D map of the occurrence of an input image. So convolution, one important thing to note is like convolution is not equivalent to transformations such as scaling or rotation. And the higher the layer, the closer the layer is to the output, the more complex the feature that is learned that becomes. So the initial layers detect edges, colors, etc. from raw pixels, and these features are used in higher layers to detect more complex shapes. And similarly, in the more higher layers corresponding to this level of feature, it will detect like more complex patterns. So we will be seeing this in the later slides, what this means exactly. One operation in CNN is like padding. So why do we need padding? So in general, we risk losing information from edges of input with no padding. And without padding in DNNs, the input to the later layer will be significantly reduced in size. So padding is generally used like to preserve image or feature sizes, and also can be used to make the feature volume of the next layer of a desired dimension. So these are mostly used in segmentation. when we are upsampling a image. So another important thing is like pooling in convolutional neural network. So, Asha, by the way, you guys have learned about batch normalization, etc. Adam, does have it has been covered, right? Yeah, so I'm assuming that you know all those things because I won't be covering in that in CNN. So that is a separate topic. Batch normalization, then other kind of things. Yeah. Okay. Okay. Yeah. Yeah. So those are like in general like deep learning concept. Okay. So yeah, so what is pooling? So pooling replaces the output with the summary statistics of the nearby output. So for example, here, what we are doing is in this example, we are taking a 2x2 neighborhood and we are selecting the maximum value. So in this 2x2 neighborhood, it will be 6. Then we will, so stride of 2 is used. We will be discussing about stride later. So stride of 2 is used, like consider it is like it is moving 2 pixel, and then it will be considering a 2x2 neighborhood. So around this area, it is like 8. So it is like having like downsampling the feature map in a same way. So pooling assists in making a representation approximately invariant to small translation of the input. So in general, pooling is used as in many cases we are concerned about the existence or presence of some features rather than their exact location. So there are like different kind of pooling techniques that are available. Like you can use max pooling, you can use average pooling, or you can even design your own like L2 norm of a rectangular neighborhood. You can experiment with different pooling, but in general, like max pooling and average pooling or global average pooling kind of thing works in when training deep learning neural architectures. So for example, again, a similar example is there. So this is the input and we are applying a pooling in 3x3 neighborhood. So what we will be doing is we will selecting a 3x3 patch and the maximum value is around 8. So there will be 8. Then we will shift it because we are using a stride of 1. Again, the maximum value will be around 7. So it will be 7. And this will go on. So these are the feature map. So now is stride. So some positions of the kernel can be skipped to reduce the computational cost. So for example, when the image size which is input to the DNN is very big. So for example, say 512 cross 512, and we are using a stride of 1, using a kernel of 3, for example. So the output will be just very, like the output feature map will also be very large. And in most cases, what happens is like some of the features will be redundant. So we are using high stride in such cases. So some position of the kernel can be skipped to reduce the computational cost. And samples are taking every, say, S grid points in particular directions. Here S equal to 2 is used. And the more they stride, the lower the dimension of the feature in the next block. So in theory, it is possible to have different stride in different directions. But in PyTorch, mostly we use like same stride across both the directions, like across height and across width of the feature. So here is an example where we are using stride in convolutional operation to reduce the size of the feature map using a stride of 2. And we can have like different dimension of kernels for generating different sizes of feature maps. So we will be looking at this in the later slides in more detail. And we can also have activations like ReLU or sigmoid to generate output from feature maps. Yeah, so here what we are doing is, so this is a 3-channel image. We are convolving it with a kernel of also like which is 3-channel. So this is like around say 3x3. Yeah. So we are getting a single channel feature map as output because each of this block will be convolved with each of this input and it will produce a single feature map as output. It's like basic dot product. And we can also have different kind of say activation functions from the feature map. So now one interesting thing about convolution is like receptive field of a kernel or filter. Just one second. Okay, so say we have an input of 5 cross 5 pixels here. We are applying a kernel of size 3 cross 3. The output using stride 1 will have 3 cross 3, the feature map. Again, if we apply a similar kernel of size 3 cross 3, we will get an output of 1 cross 1. So what happens is like this 5 cross 5 is shrunk to 1 cross 1 using two 3 cross 3 kernel in parallel. So the number of parameters for this operation is around, say this is like, so this have like 9 pixels. So 9 into 2 plus 1. So since there are like two kernels, so 9 into 2 plus 1 plus 1. So one for bias for this kernel and one bias for this kernel. So it will be like 20 parameters. But if we just apply a 5 cross 5 kernel to the input, we will directly get a output feature map of size 1 cross 1. So what is the difference between these two is like we are getting the same sort of receptive field using applying two 3 cross 3 kernels as like applying a 1 5 cross 5 kernel. So the parameters for the first case is like 20, but when we are using kernels of larger size, the parameter size also increases. But the receptive fields is like almost same, like is the same actually. So these are like examples of different type of convolutions that is happening. So using like padding 0 stride 1, padding 1 stride 1, padding 0 stride 2, padding 1 stride 2. And this is the input, and the darker region inside the input is the like patch which we are selecting, or like for kernel. Yeah, this can be called as kernel. And so this is the like dot product of the kernel and the patch of the input. And this is the output feature map. So these are showing different examples of convolution that are taking place. So here we are using a padding size of 1. Like we are zero padding it. Like each of the pixel will be having the intensity of 0. And similarly here we are using like a stride of 2. So different kind of feature map will be there. Similarly, more examples on padding and convolution. So here what we can see is if you are increasing the size of the padding, the output feature map dimension will also be increased. Okay. So another interesting type of convolution is like dilated convolution and transpose convolution. So dilated convolution is like we are dilating the input and then convolving it by applying some padding. So this was introduced in a particular architecture called as DeepLab v3. This is also called as Otrus convolution. What the main purpose of this convolution is that it reduces the computation cost. And there is another kind of convolution. So this part, so this is the transpose convolution. What it does is like if we are wanting to upsample a block, we are doing transpose convolution. Say, for example, this is the input and this is the kernel. And we will take the first element, we will multiply each of this element like a simple dot product, and we will get the output. So first this region will be 0, 0, 0, 0. Then 1 with this kernel will be like 4, 1, 2, 3. And then we will be adding each of the values to get transpose convolution. So in general, like operation in CNN that increases the spatial dimension, height and width of its input map effectively by upsampling the data. Now is the important part that is like parameter calculation and like feature dimension calculation in CNNs. So yeah, so we will be considering the dimension of feature maps as input and calculate the number of parameters for a particular convolutional layer in this kind of examples. So in general, even in PyTorch, how the data is represented or feature map is represented is by B cross C cross H cross W, where B is the batch size, C is the number of channels, H is the height of the tensor, and W is the width of the tensor. So there is a formula to like directly compute the output feature map, but I generally don't recommend to memorize this formula. So these are like mostly easy, like intuitive. So the feature dimension here, this part is the height, this part is the width. And if there is more number of channel, we can consider this dimension as the channel. And if there is more number of batches, like this thing only repeats. Like this is a batch size of 8. Like this block is like, yeah. So this is not the same block. Like this can be like different block. So when you are dealing with CNNs in not necessarily CNNs, when you are dealing with computation in GPU, you are using a more batch size to get more, like harness the compute power of the GPU more. So, okay, so these examples are taken from Stanford lectures. So some of the example that I will be going. So you can see CS, I think 3 or something, I guess. So this is like, there is a particular course for convolutional neural network in Stanford. So you can go through those examples for parameter calculations from there. So here what we are doing is, this is the input volume, 1 cross 1 cross 1 cross 3072. So batch size of 1, channel size of 1, height of 1, and width of 3072. And this is a bit non-standard, I would say, because the kernel is of higher dimension than the input. So here the kernel size is 1 cross 10 cross 1 cross 3072. The output will be 1 cross 10 cross 1 cross 1. So what is happening, if we just visualize this, is this block will be convolving with this part of the kernel, and it will have a single element, say 1 here. So this will be contributing to 1. So again, this block will be convolving to the next block in this channel. This will again contribute to another 1, and this will keep on stacking. So this will be like 1 cross 10 cross 1 cross 1. So the number of parameters for this operation is like 1 cross 10 cross 1 cross 3072 plus the number of channels in the output. So number of channel is around 10. So there will be a bias of 10, since the number of filters we are using is currently 10. So let me show this. Let us. Uh, so we can also use like, so in general, what happens is, if you are confused, like you are doing a numerical and you are confused, like whether this is what we are doing is correct or not, we can use some tools to check the dimension of the feature volumes. So for example, we are using some libraries like Torch Summary GraphVis, which will help us understand this better. Okay. So let us load. Install it. So this
Hello.
example is like, hello, yeah.
No, sorry, there was a little bit of disturbance. It's okay.
Okay. Okay, so for this example, what we are doing is, we are selecting this one. So either you can like write a class, but since this particular example is a bit non-standard, what we will do is we are not using class. We are just like using in channel, out channel, and we will calculate the parameters using cont2d here. Okay. So yeah, so for this example, we are getting 30730. So let's see. Yeah, okay. So this example has a parameter count of 30730. A bias of 10 is added. So if we perform convolution in PyTorch, we will get the similar results. So let's take another example that the input is like 1 cross 3 cross 32 cross 32, and a kernel size of 1 cross 3 cross 5 cross 5 is applied. So when this is convolved with this input, the output will be 1 cross 28 cross 28. So how this is happening is like, say, for example, I am taking this. So this is a 3D input, since it has like 3 channels, so 3-dimensional volume. So here I am showing it in 2D. So first, on the top left side, we will consider a patch. We will consider this kernel and we will multiply it. We will do the dot product. It will produce 1 pixel as output. Similarly, so this thing will shift 1 pixel and do the same operation. So when we are considering an input of size 32 and we are considering a kernel of size 5, there is like 27 more operations needs to be done, right? If you just subtract 32 by 5. So this multiplication will contribute to a single element in the feature map. So since there are like 27 more operations to be done, so the output feature map will be like 28 pixels across the width. Similarly, it will like go on sequentially for across the height also. It will be around 28 on this dimension as well. So the output feature map will be 1 plus 28 plus 20. So what is the number of parameters for this task? Parameters is like for each of this kernel. So this kernel will have a single bias because the output is of dimension 1. Like the channel in the output is of 1. So this will have a bias of 1. And the number of parameters will be like all the elements of this kernel, like 3 cross 5 cross 5 plus 1, which is 76. So if we see in PyTorch, so we can create a class using say con2d, where input channel is 3, output channel is 1, kernel size is 5, stride is 1, and padding is 0. Like the same example. Oh, I see. This is not showing this one, right? Wait a second. This is can you see what is like displaying in the meet? Because this is showing different thing. Like I am sharing the Colab notebook. Is it like showing the Colab notebook in meet? Yeah, but here it is not showing actually. Okay, like those of the guys who have laptop, you can also join in meet also, like because some form of delay is there, and so I am showing a Colab notebook in meet. Like, yeah, this one. I have to like should I
extended screen or what? You can
yeah, it was an extended screen only.
Can you check the system settings? This is display on
Where is it?
settings. And default is it? It's okay. It is showing this one. I think yeah, Microsoft PowerPoint Teams are on this side, right? Yeah, I think it should be visible.
But here it is not visible.
Can you move that? Yeah, it is extended. Right? Yeah. So you will have to move this screen to extend. Can you move this screen to that side?
No, this is not extended. This is like the same screen is relayed over there, I guess.
I don't think so. It is the same screen.
Change.
Yeah.
So extended display.
Display, yeah.
Okay. No.
Now just move that screen to that side.
This one?
Yeah.
Uh-huh.
Just move that screen to that side.
Mhm.
It is not?
Nope.
Stop extending. So
Now it's
it's
totally
not-
gone, no?
yeah,
Oh, wait a second.
yeah. Can you just Yeah. The entire screen start mirroring. Still the same.
Can we just share the whole thing, like whichever I'm getting here in there?
See the case.
Mirror this window, I guess, or maybe mirror all application windows, I guess. I think should work.
Yeah.
But this is again.
But if you go to that screen, I think right now it is showing that.
Don't think so. Okay, so is it like visible on the Meet? Like, can you see this one? This notebook? Not visible? Hmm, just 1 second. Okay?
You change content.
Yeah, auto yeah.
No, you are still in the meeting.
Mm-hmm.
You're still in the meeting.
Okay.
Just have to change the content. Yeah. Just choose content.
Choose content.
And entire screen start mirroring.
Okay. Oh, okay.
Yeah. Now just share the screen here as well.
It is visible, I guess.
Yeah, just share the screen here as well.
Okay.
In the meeting, share.
Share
And here,
screen.
yeah.
Okay.
Yeah, now this process.
Is it visible in the class?
Yeah, it wasn't visible in the class. Like so the presentation was visible, but the notebook that I was showing wasn't visible in the class.
Right.
Yeah, now it's visible
Now
here
it
as
is
well.
visible.
Yeah, now it is solved.
Okay.
Yes. So say for example this one, let me see. Okay, I think yeah. It's solved. Okay, so for example, when we are considering this input and we are convolving with a kernel of size 3 cross 5 cross 5, we are getting an output of dimension 1 cross 1 cross 28 cross 28. So the number of parameters for this operation is 76. So how, if we want to confirm using PyTorch, if this is like same or not, say here what we are doing is we are taking a class. We are having only one layer in that class. So this is the definition of conv2D in PyTorch, and we are doing a forward with this conv layer, and we are inputting it to the model, and we are doing a torch summary, and we will see that this layer will have a parameter of 76, and the total parameter will also be 76. So if we want to see the actual volume that is being passed through the conv layer, we will see that 1 cross 3 cross 32 cross 32 is like downsample to like 1 cross 1 cross 28 cross 28. So this is the conv. So yeah, so if you guys want to practice more about this, you can use these tools, which will be shared later. So this is important, like parameter calculation is mostly important in any kind of deep learning settings. So now what we are doing is like we are taking the same input, but here in this case, we are taking 6 filters. Like previously it was 1 cross 3 cross 5 cross 5. Now we are using 6 cross 3 cross 5 cross 5. So the number of parameters will change accordingly. So how it is changing is like the bias will be 6 since we are using 6 filters, and the remaining stuff will be same. So this will be 6 cross 3 cross 5 cross 5 plus 6, which is like 456 parameters for this operation or for this layer, if you can call it as a layer. So each of this convolution, each of this kernel will convolve with the input volume to give one feature map. So this will convolve here to give this kind of feature map. This will convolve with this to give this feature map. So the output volume will be 1 cross 6 cross 28 cross 28. Previously, it was like a single channel output, 1 cross 1 cross 28 cross 28. And since there is like 6 kernels, it will be like 1 cross 6 cross 28 cross 28 for here. So yeah, if we want to confirm this, like if this calculation is correct, you can always refer to PyTorch. So this is how you define the class using like input channel is 3, output channel is 6, kernel size is 5, stride is 1, and padding is 0. And we will see that the summary, the parameters for this convolution operation is 456. Similarly, if you want to see the actual volume, how it is changing, you will see that 1 cross 3 cross 32 cross 32, when applied a conv 2D, we will get 1 cross 6 cross 28 cross 28, which is like similar. Yes. And there is another problem. So the presentation is not showing here.
Presentations.
Yeah, presentation is like going blank.
This one.
Okay. Okay, so now similar example, but with a batch size of 2, we will get an output dimension of 2 cross 6 cross 28 cross 28. Since each of these 6 filters will be convolving with this to give 6 output, and each of these 6 filter will be convolving with this to give this output. So the parameters will be same essentially, but the output dimension of the feature map will be different. So it will be like 2 cross 6 cross 28 cross 28. Yeah, so since we are having a bit of problem, I will be showing the PyTorch code all at once later. Okay. So now we will be seeing like just trust that this is okay. Like we don't need to confirm. We will confirm it all at once later. So the input image is of like 1 cross 3 cross 32 cross 32, and a kernel size of 6 cross 3 cross 5 cross 5 is applied. So if we are applying this, the output volume will be so 3 cross 5 cross 5 will be convolved with 3 cross 32 cross 32. And since there are like 6 of this kernel, the channel size will increase. So we will be getting an output of 1 cross 6 cross 28 cross 28. So 1 is for batch, 3 is for channel, this 6 is for channel, 28 is for height, and 28 is for width. Again, on this layer, if we are applying a kernel of size 10 cross 6 cross 5 cross 5, so the kernel dimension is, so the channel is like 6, and we are applying 10 of these filters, we will be getting an output feature volume of 1 cross 10 cross 24 cross 24. So what happens is this 6 cross 5 cross 5 is convolved with 1 cross, the 6 cross 28 cross 28 to give like 1 cross 1 cross 24 cross 24. But since there are 10 of them, this will stack up to a channel of 10. So the final output will be 10 cross 24 cross 24. So again, like the number of parameters will be like for this for this filter will be like 6 cross 3 cross 5 cross 5. Plus, since there are 6 of these filters, the parameter will be like the bias will be added as 6 for this layer, and for this layer, it will be 10 cross 6 cross 5 cross 5 plus 10. So since there are like 10 filters, 10 this one, a bias of 10 will be added. So the total parameters for this layer, like for this 2 operations, not layer, like 2 layers, will be like 1966. Okay, so another interesting thing about convolution is we can use 1 cross 1 convolution. So what does this like 1 cross 1 convolution does is it will like create a bottleneck. So convolution of C cross 1 cross 1 transforms an input of volume of 1 cross C cross H cross W to 1 cross H cross W. Hence, we can apply any number of such convolution to shrink or expand the input volume. So in certain cases, we will see that we do need to shrink the volume. In such cases, we will apply 1 cross 1 convolution. So the input size of 1 cross 64 cross 56 cross 56, when convolved with 32 of this 64 cross 1 cross 1, we will get like 32 of 56 cross 56. Say, for example, this block is like 64 cross 1 cross 1. This block will be convolved with each of this to get a one channel input, 1 cross 56 cross 56. And since there are like 32 of this, so if this was an animation, it would have been better, like good to explain, but just visualize it like this. Like this block is convolving through the whole volume to give a single one, like 2D one channel output feature map. So similarly, like 32 of this will be stacking up a 32 channel feature map. Yeah. So now let's look at an interesting example where we take a convolutional neural network, fully connected convolutional neural network, and we break down how to calculate the feature volume and the number of parameters of each of the layers present. So when you are designing like complex neural network architecture, this kind of mathematical formulations will be essential, because in PyTorch it doesn't like supports, like in Keras, if you are using this kind of convolutional neural network, it will just assume the output volume and feature dimension. But in PyTorch, they doesn't assume the feature volume, like how you want to take the input to a particular feature or how you want to output a particular volume. So for this, what I think, yeah. So for this, this is the definition. In the definition, what happens is we are wanting to say what kind of layers will be used. Say we are defining con1 layer, which is con2D, then con2 layer by con2D. You can use different kind of padding, whatever will be the input size, whatever will be the output channel, whatever will be the kernel size, you can just define it. You can refer to the PyTorch docs for this. And this is the bash norm 2D, max pool, flatten, etc. You can like define. And this is the activation sigmoid. We are using sigmoid. So for the first layer, what happens is, say for example, we are inputting a volume, feature volume of size 1 cross 3 cross 7 cross 7. Consider it as a like image, like 7 cross 7 image of 3 channel. So the first layer is like con1 layer. So con1 layer, it takes an input channel of 3 and output channel of 3. So, and it also has a padding of size 1. So when we are applying a padding, it will be padding top, bottom, left, right. So 7 cross 7, like height of 7 cross 7 will turn into 9 cross 9, because left side 1, right side 1, which actually makes the width of dimension 9, and top and bottom 1, 1 means it will make the height also 9. So firstly, we will be applying the padding across the height and width, and the number of channels will be the same, that is 3 for this. So after we have applied the padding, we will be applying the kernel. So kernel, what it is assuming is it is kernel size of 3. So 3 cross 3 kernel will be applied here. And output channel is also 3. So the output feature volume will also have a dimension of like 3 in the channel. And this is first one is the batch size. So batch size is 1. So if we input a batch size of 4, the final batch size will also change to 4. So how we are doing it is like we are using a stride of 2. So this input volume. So input volume after the padding is like 1 cross 3 cross 9 cross 9, and a kernel of size 3 cross 3 will be convolved with stride of 2, and the output will be like 1 cross 3 cross 4 cross 4. So in 2D, what is happening is, say for this is the padded input. We are taking this 3 cross 3 kernel. We are getting a output of 1 pixel here. So then we are again moving it by a stride of 2, means 2 pixels to the right. Then we will again do a convolution. We will again get a feature volume. Again, it will move a stride of 2, and again it will get a feature volume. And again it will move, and it will be the end of the image, and it will have the first row, that is 4 pixels here. So the number of parameters will be, so since there are output channel is like 3, the bias will be 3. And the number of parameters will be like the number of elements in the kernel. So since this is a like 3 cross 3 cross 3 cross 3 kernel, the number of parameter will be this one, 84 for this. So in the second layer, so this is the first layer. So in the second layer, we are applying a padding of size 3. Hello, is there any question?
No, I guess.
Okay. Yeah. So in the next layer, what we are doing is we are applying a padding of 3. So we are taking the feature volume, which is 1 cross 3 cross 4 cross 4. So here I am represented in just 2D, but it is a 3D volume since it is having 3 channel. So we are taking this input, we are padding it. So the final, after the padding, the volume will be 1 cross 3 cross 10 cross 10. So padding of 3 means upper, it is applying a padding of 0 padding of 3, which means like 3 on the upper, and then there is this 4 pixels in the middle for this content and 3 on the lower. So 6 plus 4, which is 10. Similarly, on the across the height and across the width, the padding is applied, and we will be applying a kernel, similar kernel, which we used here. So finally, the thing is like we are using a stride of 1. So we are not using a stride of 2 in this layer. So this will be convolving, it will be producing an output, it will be shifting by 1, it will be again producing an output, it will be again shifting by 1 till the whole image is parsed, and we will get a 8 element, like 8 element across the width and 8 element across the height. So the parameters will be same, that is 84, but the feature volume will be different, 1 cross 3 cross 8 cross 8. Previously it was 1 cross 3 cross 4 cross 4. So the padding dimension will change the output of the feature volume. Now we will be applying batch norm 2D. So batch norm 2D is like standard thing applied. I hope that you guys know about batch norm 2D, like it has been taught, I guess. Yeah. So batch norm 2D, it has what it does. So it has like 2 parameters, that is gamma and beta. So the number of channel that we have for that layer will be the number of parameters for that batch norm 2D. So here for gamma, it is contributing 3, and for beta, it is contributing 3. So number of channel into 2 is the number of parameter for batch norm 2D. So the batch norm 2D doesn't essentially changes the volume since it is just doing a batch normalization. The parameter will be like 6 for this layer. Similarly, for max pool 2D also, we will see that so max pool doesn't have any kind of parameters of itself. It just like downsamples. So parameters for this layer will be 0, but when we are using max pool 2D, the output feature will shrink, like 1 cross 3 cross 8 cross 8 will go to 1 cross 3 cross 4 cross 4. So we are on this layer. Next is flatten. Flatten also doesn't have any extra parameters. So the number of parameters for this layer is 0, but it will change the dimension of the input volume. So 1 cross 3 cross 4 cross 4 will be 1 cross 48. So what flatten does it flats the block to make it compatible as an input to a fully connected layer. Now we will have a fully connected layer, FC1. FC1 is like linear, NN dot linear 48 to 10. So input will have 48, output will have 10 for this layer. So the number of parameters will be the total number of connections. Since it is a fully connected layer, each of these neuron on this layer will be connected to each of this neuron on the other layer. So the total number of connections will be 48 plus 10. And the number of bias terms will be like 10 for this layer, since we are considering this layer, 10 neurons in this layer. Yeah. Again, there is batch norm 1D. So we are almost at the end of this neural network. So batch norm 1D, it also has like 2 into 10, since 10 is the number of feature volume, and it has like gamma and beta parameters. So the number of parameters will be 20 for this layer, but the input dimension and the output dimension will be similar. And then there is the last layer, which has fully connected layer. So 10 to 1. So we are using out as the layer. So out is NN dot linear 10 to 1. So 10 as input, 1 as output. So each of these 10 neuron will be connected to this one neuron. So the since it is connecting to this one neuron, the bias will be 1, and number of connections is like 10. So total number of parameters is 11. So the total number of parameters for this whole neural network is around 695. So this is how you like calculate parameters for a neural network. And this is a very simple one. In general, you will be inputting images of size 256 cross 256. So now I think I can show you the Colab notebook. Yeah. In this collab notebook, what we will see is this is the input. I think this is not visible, right? Yeah. Okay. In Teams, it is visible. Oh,
Yes.
no,
No, collab
the
is not
collab
visible,
notebook.
the slide.
Oh, okay. Slide is visible. Collab notebook is not visible.
No.
Oh, acha, let me do one thing. Like, I will be sharing the collab notebook later on. You just go through the collab notebooks. Okay, again, the same problem is happening. Like the presentation is not. Oh, okay, now it is showing.
Yeah.
Some glitching is happening. Okay, so now let's look at the feature learned by the CNN. So features that is learned by the CNN are like there is a paper. You can refer to the paper in this slide here. So what they did was they wanted to see how the so these are the like visualization obtained by passing an input image through a trained CNN and then selectively projecting activations back to the image space using a deconvolute. So they have proposed a like deconvolute kind of architecture, which they see which part of the image or which features are being detected. So the initial layers, which are close to the input, they just detect edges, color, or low-level features. Like it is like similar to the first experiment that we have seen, like on the Hubble and Wiesel. Similarly, the mid-level features will have mid-level layers will have mid-level features, and those features will be specifically like so what they did was like they used the stored max pooling indexes to put feature back into their original locations and then inverted the convolutional ReLU layers to reconstruct with the image patterns activated specific neurons. So there is some bit of complexity in this. Like you can read the paper to see what exactly they have done. But the final result of the paper is like the higher layers, that is the closed, the output layer responds to the object parts or the entire objects or problem specific features, and the initial layers they respond to the like lower level features like edges, color, or etc. So some of the architectures that are like these were popular back in 2014, 2015 in that era. So this is VGGNet. So VGGNet is from I think Google. So it is significantly deeper with 16 to 19 layers than AlexNet, which had initially 8 layers, and it had around 140 million parameters. So it had around 7.3% top 5 error. So what they did was they used small filter sizes, a stack of 3 cross 3 conv stride 1 layers with 30 parameters has the same effective receptive field as 1 7 cross 7 layer. So this thing we have seen in the previous slides, like the receptive field. So they exploited the receptive field part, like they are stacking more smaller convolutional filters to make more representation, like good representation using smaller, like lower number of parameters. So they made deeper networks with lesser parameters. The more deeper, the more nonlinearity it captures. So they used ensembles, features of deeper layers, and they like found that the features of the deeper layers generalizes well to other tasks also, and trained on 4 NVIDIA Titan Black GPUs for 2 to 3 weeks during that time in 2014 or so. And what they reinforced is that the notion that the CNN have to have a deeper network of layers in order to in order for the hierarchical representation of visual data to work. So the more the deeper, the more representation it like captures. Next is GoogleNet. GoogleNet, what it did is like they had like 5 million parameters, and they also achieved the top 5 error of 6.7% using only 22 layers. So this previous method used around 16 to 19 layers, but they used 22 layers. So what they did was they found that uh, when we are increasing the number of layers, the parameters also increases. So we have seen that 1+1 convolution in the previous slides. They are creating a bottleneck to reduce the number of parameters using 1+1 convolution. And they were also using a parallel combination of different kind of receptive fields, like 3x3 receptive field, 5x5 receptive field. Then there is like 1x1 convolutions. And they use like all these receptive fields in parallel. And so this was their contribution. In this way, they like decrease the number of parameters while also increasing the number of layers. So till now, the assumption was that as we keep on stacking more layers to a deep neural network or CNN architecture, the accuracy will improve. But later, what happened was in the next challenge, the Kaimihi and group, what they found was like, as we go on stacking more layers, it is harder to optimize. Like for example, here if you can see, like 56 layer convolutional neural network has high validation error than a 20 layer neural network. So it is like not overfitting. It is actually like problem of vanishing and exploding gradient. So what they did was like they took a layer and they added this with the next layer. So deeper model should learn at least as good as the shallow layer, copying the learned feature from shallow model to and setting the additional layer to intensity to identity mapping. Like this was their contribution. So what they found was that it is becoming easier to optimize deeper layers. Like they used about 152 layer model, and this was the first architecture which surpassed the human level. So human level have top 5 error of like 5.1%. So human level error occurs because of the ambiguity of images and occlusion, all those traditional things like found in images. So this architecture was the first one which like solved the ILS VRC challenge by giving an error rate of 3.6%, top 5 error. So this is like still some versions of ResNet are still used to date, like used to even today. Just one second. So yeah, now there is like transfer learning in CNNs. So training a CNN model from scratch is very difficult. Like back then it was difficult. Now we have a lot of GPUs. We can just fine tune the whole model, CNN model. But in certain cases, what happens was like we needed a very large data set. So they will be training for 3 months, 4 months, like if the data set is increasing. So well-known architectures takes weeks to train using multiple GPUs, not like single GPU. So the inspiration is like low-level features such as edge, corner, color blob, etc., generic, which are found in all of the models. So high-level features become more specific to the dataset or the classes that the original dataset was like all the original model was trained. Like these are like problem specific features. High level features are problem specific features. And the extraction of features, what it does is like we can remove the last fully connected layer, but treat all the other layers as fixed. And on passing a new data set yields a feature of fixed dimension for each example. So use the resultant features to train a new classifier. So what transfer learning means is like we can reduce the redundancy by taking the already learned features in some different problems. So transfer learning is currently used like widely, like zero shot, one shot, and in LLMs you are just prompting it. Yeah. Yeah. So GPT, like there are not, I think, large model for like is for images. What they do is they are using transformers. So there are vision transformer kind of models. So I'm not sure about that because I just mainly work on CNN, but there should be. So there are like segment anything model SAM. So those are called foundational model, I guess. So foundational model, what they do is like they are training on a whole set of data. They're compressing all the data and they're interpolating it pretty well to other tasks. So that is the thing. So fine tuning a CNN model. So we fine tune the weights of the pre-trained model using backpropagation, and the whole network or some higher layers close to the output can be fine tuned. So this is a like general table or chart you can say, which you can follow for fine tuning or transfer learning for CNN. So generally what we do is like, we don't follow this kind of chart. Like this is a very well-known chart, which was previously very famous. What we do is we see the validation accuracy or matrix which we are calculating, and accordingly we fine tune some of the layers, like in applications. But here, if you like follow the chart, like there will be like similar, like a model which is trained on a large data set will have similar downstream task, which you can call, or a different downstream task. So certain layers will be, we will select certain set of layers to fine tune those models. So this is like in general transfer learning. Now we will be seeing the demo. Demo is for multi-class image segmentation, but I need help. Yeah, so I will be sharing the Colab notebook. So it should be visible, right? Okay, so I will be covering the slide. There is only 3 slides left. And I will be just going through the code now for the multi-class segmentation. So for multi-class segmentation, we have used, yeah, just give me 1 minute. Yeah, 2 minutes. So multi-class segmentation, we are using Res Unit plus architecture, which is a very famous architecture for colonoscopic segmentation. So they use residual unit to make deeper networks easy to train, and skip connection helps to propagate the information without degradation. They have also used like squeeze and excitation block. Like each channel is squeezed using a global average pooling for generating channel-wise stats. And then second step, it is excitation for active calibration. So squeeze and excitation block, this is a like individual paper. Right, residual unit is also a individual paper, which we have seen. It's proposed by Kamini. Then res unit was also a paper. So this architecture takes all the paper, combines it and compresses it into a single architecture to make it like faster, efficient to train. Then it also uses Orthrus spatial pyramid pooling module, which is like dilated convolution, so to train it faster and like to have more efficient training. So all these things are packed into an architecture of 4.06 million parameters, which is very low. Like in general, if you are using like GPT kind of model, it will be like 7 billion parameters. This is very, very low, but it works quite well. So this is the problem statements. So we are having wild plants. We will be segmenting the wild plant. So input will be 256 cross 256 cross 3, since this is a color image. So 3-channel image will be input to the res unit plus model. The output will be softmax layer, since like there are 3 classes. So sigmoid won't work, right? So either it will be, each of the pixels will either be classified as black, which is like background, which is the majority part of the dataset. We will be seeing this, or it will be classified in class 1 of wild plant, which is red. So class 1 of wild plant have certain characteristics, and class 2 of wild plant have certain characteristics. So we will be seeing that if our model is able to segment this part of this wild plant better. So yeah, so the 2 metrics that we are using for this is like dice coefficient and intersection over union. So these are set-based metrics. So intersection over union, what it does, it is also called as Jaccard. So it is calculated like this, and dice, it will be like taking the overlap region, and we will be dividing it by the predicted and the ground truth. So both of these metrics, the closer it is to 1, it is better, and closer it is to 0, it is bad. So we will have like train, validation, and test function, and we will have all those things which we will be doing. So now let's like look at the code. Yeah, I need help. I think it is visible, right?
Yeah.
Wait a second. Yeah, okay. Runtime. Yeah, sometimes this is working, sometimes this is not working, like weird. Okay, so we are firstly installing all the required libraries, like which are not present in Colab, like gdown for downloading any kind of data set from Drive. If you are saving it in Drive, we can download using gdown. We can use Colorama to show different color of text. We can use TorchViz and TorchView to see the graph of the model. Then we can use torch summary to summarize the individual layers, the parameters of the model, etc. So we will be installing this library. We will be downloading the dataset first, and we will be unzipping the dataset. It's visible. So it is currently downloading it. So some of the imports. So these are the general imports that are already found in Python. You can use it. These are the PyTorch based imports, and these are the like graph based or visualization based import. and we are also seeding it. So there are like two types of seed present in the script. That is random seed, which will like there will be consistent split in the train or test, and then there is NP's random seed, and there is another kind of seed that is present, that is torch seed. We are not using torch seed here, but it won't matter that much. So we have downloaded the file. In the script, what we are going to do is we will see the statistics of the dataset. We will figure out that most of the dataset, when we are performing the segmentation, the mask, like 80% of the mask will be covered in background. Only like 10% will be covered in class 1 and 10% will be covered in class 2. So this is a like highly imbalanced like segmentation problem. So in general, segmentation problem is mostly imbalanced. So it is computing the statistics. It will take around 2-3 minutes. So let me go over other code also. Okay. So here what we are doing is we will, once this thing is downloaded, and yeah, it is downloaded. And yeah, so yeah, once the statistics is computed, we will just create separate folders for training, validation, and test images. So we will have separate folder for train images, train masks, validation images, validation mask, test images, test mask. How we are dividing it is into 60% for training, 10% for validation, and 30% for testing. So this is like common. This is how we divide if we have a new data set. Okay. This haven't been done. It's 50%. Okay. Okay, let me go through this code. So if we run this cell after this thing is done, we will find that this like first 5 samples of train set will be like this. This is the input image, this is the mask, and this is the overlay. Since in segmentation, we like to see how it is actually overlaid. These are the first 5 samples of the validation set, image, masks, and overlays, and first 5 samples of the test set. Now is the ResUnit++ architecture. So ResUnit++ architecture has a paper. So this is mainly used for colonoscopic segmentation in medical images. And you can refer to this paper. I will be sharing with you all this notebook, etc. You can refer to this because. So I have copied this code from their original implementation, which is found in this link. So they have like squeeze and excitation, then stem block, then resonate block, then ASPP modules, and attention block. It even had self-attention module for convolutional neural network. So this is different from transformer-based attention. Then there is decoder block, and there is ResUnit++, which combines all of these methods. And I think, okay, it's 87% done. Let me just run this first.
Okay, any question from the class or offline?
Yeah, any questions, by the way? Okay, so the whole dataset statistics have been computed. What we can see is the background is having this many pixels. So this dataset is already augmented, right? We are not doing we are not doing augmentation on the fly during the script. This is already augmented. The background is having this many pixels, which is like 80% of the dataset. Class 1 is having this many pixels, which is like 9.39, which is 10%, and class 2 is like 10%. So this is a highly imbalanced dataset. So this is actually a difficult problem, like mostly mid-level difficulty, not too of a difficult. Like there will be occlusion also in this kind of settings, but let's see how it is performing. We are splitting into like train, validation, and test split, and we will have separate folders. So we are splitting it in here. So in general, if you are trying to run this script on Google Colab, you won't be able to train it for like 100 epochs, because I think Google Colab has a limit of 3 hours or 4 hours nowadays. Previously, it was giving around 8 hours, like during 2019 or so. Yeah, so we can visualize the actual test splits. Yeah, these are the splits and overlay, and this is the model. Okay, so now, like channel-wise summary of the model, if we are passing a input of size 3 cross 256 cross 256, which is the input image, we will see like each of these layers will have different kind of output and parameters. So the total parameters of this model can be found out here using like, this is like 4.06 million parameters, which is like 4.07 million parameters, you can see. And you can also render this whole model into a graph. So this kind of rendering is essential when you are developing new kind of models, to see how the feature maps is going, how the input and output are connected. So you can go through this kind of rendering. This is an essential tool. And lastly, at the output, we will see that we are using a softmax layer. Here it is written softmax. And this is the data generator. Data generated, what it does is it will uh, pass input image, the corresponding ground truth mask, and the file name, since we will be saving the inferences once this is trained. So this is the part where we compute the dice coefficient using the formula. So these are standard metrics. You can find that, but here I am computing it by taking the source code. This is IOU, and this is the categorical cross entropy loss. So we can define categorical cross entropy loss either by NN dot categorical cross entropy, or we can define it like this also. And this part, what it does is it creates the color map and apply the overlay, like creating the color map, applying the overlay of the final predicted segmentation or ground truth. This is just a sanity check to see if all the images are present, and this part will like load checkpoint and set checkpoint. So now we are coming to the core method, that is training method. So training method has like model.train, which sets the model to update the weights in training mode. Then there is like optimizer.zeroGrad. So here we are doing model.train. We are doing optimizer.zeroGrad to clear the gradient from the previous pass of the computational graph. So there will be different, like there will be multiple passes, like since there will be like multiple steps for particular epochs, and we will be doing optimizer.zeroGrad every time. Then there is loss.backward, which does the back propagation like by itself. And then we will step the optimizers.step. And in the meantime, while doing all this, we will pass the input and ground truth to the device, that is the CUDA or the GPU. Since all this computation will be done in the GPU, and there will be like, we can accommodate many batch size. We will be getting the predicted output, and we will apply the softmax. I think softmax wasn't done in the model. Oh yeah, softmax will be here. Softmax is done in the model. We can apply softmax for predicted probabilities as well. And we can also calculate the loss. And we will compute the loss. We will accumulate the loss across each of the epochs, and we will dump it at the end of the epoch. So this is the training epoch. Now there is this validation epoch. Validation epoch is same as the training epoch, just the difference is there will be model.eval, and we won't be backpropagating any kind of weights. So we are just passing the whole validation dataset to see how the training has been done. And for test epoch, it is similar to the validation epoch. The only extra thing that we are doing is after training for say 100 epochs is done, training and validation epochs have been done for like 100 times. We will, at the test epoch, we will see the final statistics, like how the predictions is there for the particular model, how the input is there, how the ground truth is there, how the predicted, how the overlay of the ground truth, etc. So this is the code for that. You will check it after the class is over. Then there is a master epoch, like train, validation, test, which controls all of this training, validation, and test epoch. So this thing synchronizes all of this. So what we can do is in this epoch, we can like have certain conditions, like after 50 epochs, we will be dumping the model. So saving a checkpoint, something like that. Then at the end, like till the whole epoch is trained, like the whole model is trained for the particular number of n epochs, we will be dumping the final test epoch statistics. So test epoch, it generally dumps the whole statistics. Then there is the main function. So main function has a certain arguments. So either you can do arg parse, which is done if you are using scripts, but since we are using Colab and in Python notebook, we are defining the arguments like a class. So here we are defining some learning rate, batch size, number of epochs. Let's say, for example, we are training for 2 epochs here. Number of classes will be 3. All these hyperparameters and folder names, etc., will be given here. Then we are defining the like train loader, validation loader, and test loader. We are calling the model. We are passing the model to the device because everything will be happening in the GPU. And we will call the master epoch. And this master epoch will coordinate with all the training, validation, and test functions to finally train. So if all the code is executed, this should essentially train. But the problem will be like if you are training this, it will take like 3-4 minutes per epoch, which is uh, very slow, I would say. So train epoch is not defined. I think I missed something here around. Oh, train epoch. It's not equal. I didn't compile this code. I think every code is compiled, right? One, tick, 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 tick. Yeah, I will take, I think, 5 minutes extra. I think it is already 5, right? Yeah, 5 minute extra I will take. So yeah, this is training. So dice and IOU are being computed, but since training will be taking a lot of time in Colab, so what I have done is I have already trained it for around 1,000 epochs, and I am downloading the models from my website, and we will be seeing that. So this plots will be showing how the training has been done for like 1,000 epochs. So these are the variation of loss, categorical cross entropy loss, the variation of dice coefficient, intersection over union. And we will be doing a test dump to see how the test metrics are there. So I won't be compiling this since this will be like taking another 10-15 minutes. So I will be just showing you the output, which is there already present. So this is the ground truth, this is the input, and this is the predicted mask. So this is the good result. So prediction is like having dice mean of 1, almost close to 1. So these are good results, and these are the overlays of the ground truth, and these are the overlays of the prediction. But let's also see the bad results. So here we can see there is some kind of mask, but we are not getting any kind of results. So there are, since this is a highly imbalanced kind of problem, segmentation problem, there will be some like some images which are having bad results. Similarly, for class 1 statistics also, they are performing quite well. And for bad results also, we are seeing that there is quite bad. And for class 2 also, we are getting all these results. So you guys can check the notebook later on and see. And the final coefficient like dice coefficient and IOU is like around 92 and 89 for the whole test data set. So this is a difficult problem, but it is quite good for segmentation. So yeah, this is it.
Thanks, Jimut. Thanks for this very contentful and practical demonstration also of the system.
Yeah.
Now, one thing, did you clarify about the difference between accuracy and precision?
Yeah, so we are actually not having accuracy in as a matrix in here, because since in the case of imbalanced data, we will see that if a data is like highly imbalanced towards a certain class, accuracy will be like kind of like not a good metric for measurement. So what we are doing is like dice coefficient and IOU, and those are like intersection, like set-based matrices for this task. And those are actually quite giving good results for the test data. And precision, yeah, precision I could take, like I could take, but here I haven't taken. So intersection over union matrix I have taken. So yeah, if someone wants to extend this code, they can try out precision also for this.
How many classes are there in the problem?
Yeah, so there is one background class, one so one kind of weed is there, like so wild plant. So there are like 3 classes, including the background.
Okay. Okay, thanks. Are there any classes from the online and offline audience?
Yeah, I think there is no questions.
Hello, I have a question.
Yeah,
Hi. So I was working on some alignment part of X-ray images and text reports.
I see.
I'm audible, right?
Yeah.
So I found that the alignment problem was very poor results, and that was mainly due to the segmentation problem in the medical images.
Correct.
And those segmentation were failing because of anatomical co-occurrences, like lungs will always be beside hearts and heart will always be beside lungs.
Hmm.
So would you like to suggest any turnaround way that how can I
Yeah,
improve alignment?
what I feel is like alignment problem. If you are using good attention mechanism, like squeeze and excitation block or some sort of attention mechanism in the convolutional neural network, the better the attention mechanism is, the better the alignment will be. So you should look at different architectures, like state-of-the-art architectures, which are performing good, like attending good to the image. Because in some certain cases, like inherently medical images are very difficult to segment, like because there are like many like clinical dependencies in the medical images. So these are like not like mostly natural images where we can distinguish a cow from a cat. So it is actually a difficult problem, but I would suggest like look at different kind of architectures, like state-of-the-art architectures, and try to figure out the how they are solving the attention mechanism in the alignment.
Sure. Yes, that was really insightful.
Any more
Okay,
questions?
if there are no more classes, maybe we should end it.
Yeah.
And on Friday again, there is an interesting lecture by Manojit Chaudhary, who is a well-known name in NLP now. Thanks, Jimut. Thanks,
Yeah.
everybody.
So I need to talk to you sometime tomorrow, maybe morning. Will it be possible? Like for 5 minutes?
Yes, after 9:30.
Okay. Okay, I will call you. Yeah.
Yeah.
Okay. Thank you,
Thank you.
sir. Okay. Bye.
Thanks, everybody. Thanks, Ravanti. Thanks, TS.
Uh,